Good morning, everyone. And today I'll be discussing the molecule as vibrating rotator and that fine structure of infrared bands. We have already discussed that vibration spectra with the help of the harmonic and anharmonic oscillator. As we are getting that the infrared bands for the vibration transitions. At the same time, within these vibrations, we'll be getting some of these lines within these bands, which are arranged in a particular fashion. Then this is called the fine structure of infrared bands. And what now these fine lines are representing the rotational transitions within these bands. Now we can not take separately this the change of that is the transition between the vibrational levels. Rather, there is a transition between the rotational bands, rotational lines also taking place within the same molecule. So, assuming that, ignoring that if there is no interaction between the vibrational level and the rotational levels, then what I could write, then once, now simply I could sum of these two energy levels, then, so this G of nu plus of F of Z is equal to omega E nu plus of half minus omega E x E and nu plus of half its square plus this is anharmonic oscillator plus B of J plus of 1, where we know that where this B is equal to h upon 8 pi square I of C is equal to h upon 8 pi square of mu r square of C. That is the rotational spacing. So this provides you, this B provides you the rotational level with a similar spacing associated with each vibrational level. A transition between the two vibrational levels would therefore be comprised with the number of transitions between these two corresponding sets of the vibrational sets of the rotational levels. So this would result in several lines within these bands, branches, and because there are two transitions between the two rotational levels, two vibrational levels, within these bands we have these rotational lines itself. So these lines would form two branches of equidistant lines. This is, however, not in agreement with the observation. As we said that in the case of once we did only the pure rotational spectra, we have equidistance spectrum, equidistance lines between the equidistance lines for the rotational spectra. However, once we are getting this experimentally, this is not agreement with that one. It means that what we are following that once we have two vibrational levels, within these we have a fine structure, that is the rotational transitions, but these are not equidistant. Experimentally we are getting something else. It means that there is, once you are looking at one side in a one band, there is the separation is decreasing, another side is separation of these rotational lines are decreasing, and on other side it is increasing. We'll see that these lines would be referred as a P branch or the R branch for the rotational vibrational spectra. So we find the shape of, if you look at the shape of my anharmonic oscillator, the shape of the anharmonic oscillator, then we have something like this. So this is R of E, and this is called the Morse curve. This is a Morse curve, which is not a parabolic, rather it is a bit distorted on the other side. So we find from the shape of the potential curve that as nu increases, the equilibrium intermolecular spacing and hence the moment of inertia of the molecule increases, so that the rotational constant B decreases. Because in a rotational one, because B I know that's 1 upon R square, if R is decreasing then it is changing. So this R is increasing, so that the obtained constant B is decreasing. Thus B will determine the spacing between the rotational levels of the different vibrational states. So now if I have two different vibrational states, then it means that the value of B will be changing. At the same fashion that once we have discussed in the case of the rotational spectra, as this J is increasing for a higher value, this B doesn't remain the constant. Then we modify that constant B. So therefore, once you will be dealing two vibrational levels, the value of B changing for both the vibrational spectra. Therefore, the rotational constant associated with the vibrational state nu is written as B of nu. So we'll be defining that this B of nu. This is B of nu for the vibrational level. And a given vibrational state, the internuclear distance and hence the rotational constant is changing during the vibrations. Therefore, we must use a mean value of the rotational constant in a given vibrational state, and we will be defining that V of nu is equal to 1h upon 8 pi square C of mu and 1 upon R square of nu, its mean. So we are defining with the help of the mean because it is changing with respect to the nu. So where this 1 upon R square is a mean value of 1 upon R square in the vibrational state nu. During the vibration, it can be shown that the rotational constant we knew in the vibrational state nu is given by simply this V of nu is equal to V of E minus alpha E nu plus of 1 upon 2 plus and so on. So now we are representing V of nu equal to V of E minus alpha of nu plus of half this with this relation. So where this alpha E is a constant depending on the shape of the potential curve, and this alpha E is very, very less than this B of E. And VE is a rotational constant corresponding to the separation RE at a minimum of the potential curve. So this BE is a rotational constant for which that is the minimum distance, that is the RE, when these molecules and intermolecular distance is RE. For that, what we are defining that this is VE, that is the B of E is equal to H upon 8 pi square I mu of RE square, where the intermolecular distance is RE. Then in that case, we are defining this B of E. So now I could write this total energy for the rotational vibrational rotator, then this Z of nu plus of J of this F nu of J is equal to omega E nu plus of 1 upon 2 minus omega E x E nu plus 1 upon 2 its square and plus V nu J of J plus of 1. Where again this now once I am defining this V nu prime will be less than to V nu double prime. Because if you look at the previous relation where I have this V of nu is equal to B of E minus alpha of nu plus of half. This B alpha is my constant. Now the value of nu is increasing, then this will be decreasing. So if I'm changing that, if I'm going for this, suppose this single prime is defined for the higher level vibrational state, then V of nu prime will be less than to this B double prime. So V nu is decreasing slightly with increasing the nu. The spacing between the rotational levels associated with nu is equal to 1 are for a slightly smaller. Once I am looking for this nu is equal to 1, that is a nu is equal to 1. In that case, slightly smaller than that between the levels associated with nu is equal to 0. If we look at this nu is equal to 0, corresponding to nu is equal to 0, if I am looking at the transitions, then this V of nu is be high, lesser for this one, and V nu for will be the higher for this one. Okay, so once I will be plotting that energy diagram, suppose this is my nu is equal to, nu prime is equal to 1, and this is the nu double prime is equal to 0. So if I'm plotting these levels, this z double prime is equal to 0, z double prime is equal to 1, z double prime is equal to 2, and z double prime is equal to 3. And once I will be looking for in this case, because B of nu is reducing, so what will happen? So the spacing in this case, the spacing between these energy levels is slightly higher as compared to this one. So this is nu, this z prime is equal to 0, z prime is equal to 1, z prime is equal to 2, and z double prime is equal to 3, and so on. So the difference between these two rotational lines will be slightly higher in this case once this nu is equal to 1, because the value of Vv is decreasing. Oh, sorry, yes, this is the decreasing, this is really less than 2. Since the eigenfunctions of a vibrating rotator are essentially the product of the eigenvectors of the oscillator and the rotator. Now, these are the eigenfunctions for the rotator, once we are talking about the rotational spectra, and the oscillator once you have the vibrational spectroscopy. So the selection rules, because we are saying that these are independent of each other, and the selection rules will be following in the same fashion that what we have observed, that this delta nu is equal to plus minus 1, that was, and if you remember that there is a transitions taking place that we are getting the overtones, then there must be a plus minus 2 and plus minus 3 and so on. However, this delta z is equal to plus minus of 1. We'll see that corresponding to delta z is equal to 0 as well. We'll see that. So for the main absorption, we have the main absorption, that's delta mu is equal to plus minus of 1. And the most probable transition, is nu prime is equal to 1, then what we are achieving from this nu double prime is equal to 0. It's most probable transitions once from nu double prime is equal to 0 to nu prime is equal to 1. The J, both are the transitions, delta Z is equal to plus minus 1 are now applicable. Now, if there is a most probable vibrational transitions taking place for nu double prime is equal to 0 to nu prime is equal to 1, then for both the cases, now this delta Z is applicable to either the plus minus of 1. Both these selections will be applying for this case. Because these two J levels involved now belong to the different vibrational levels. Because if you remember, once we will be discussing only the rotational spectra, pure rotational spectra, delta J either it is a +1 or the -1. Now in that case, this delta J plus -1 both are applicable because we are dealing two independent vibrational levels. We are dealing with two independent vibrational levels. So for a given vibrational transitions, vibrational transitions, if delta J is equal to +1, gives the set of lines called the R branch, then this represents the R branch. And if this delta J is equal to -1, this refers for this P branch. These lines corresponding to delta J is equal to +1 is a R branch, and delta J is equal to -1 is equal. This refers for the P branch. All the lines of both the branches form a vibration rotation. So the wave numbers of the branch lines of a particular band, nu and nu double prime. So we'll be representing now for both the branch. Let's see now again. I will be writing that this nu is equal to, that is the Z of nu single prime plus of F nu prime of J prime, because it's a vibrational rotation, minus Z of nu double prime plus of F nu double prime J double prime. So putting these values, then you have Z nu prime minus Z nu double prime plus B of nu prime J prime of J prime plus of 1 minus B of nu double prime J double prime of J double prime plus of 1. And once we are solving it, it's very simply, we'll be getting that nu of naught plus B of nu prime of J prime plus of 1 minus B of nu double prime J double prime plus of 1. So where this nu 0 is equal to, we have this Z of nu prime minus Z of nu double prime. In place of this quantity, we replace this nu of 0. And this is the wave number of a pure vibrational spectra, for which, now this is a pure vibrational transitions, for which this J is equal to J double prime is equal to 0. This delta J is equal to 0, one can say. And for this transition, once we are taking that is just a pure rotational, this delta J is not equal to 0, this is not allowed in this case. So, and the corresponding to the missing lines in the band, nu is known as the wave number of the band region. So this is called the band region. So means that corresponding to this nu prime 1 and a nu double prime is 0, and it is from the 0 to the another vibration level 0 to 1. So in this case, this delta J is equal to 0. This delta J not equal to 0 allowed over here. So now once I have this one, now if in this relation that we'll see that once the delta J is equal to +1 and the delta J is equal to -1, we'll see that. Now first we'll be discussing that this R branch. And I said that for the R branch, delta J is equal to plus of 1. Means is equal to J prime minus J double prime is equal to +1. And this means that this J prime is equal to J double prime plus of 1. So if I would like to find out the wave number corresponding to the R branch, then simply putting that in place of this j prime, you need to put the z double prime plus of 1. Then simply nu of r, that is the r branch, is equal to this nu of naught, that is the pure vibrational frequency, plus b of nu prime, and this j plus double prime plus of 1, j double prime plus of 2, minus b of nu double prime, j double prime, j double prime plus of 1. And simply you expand this is nu 0 plus b of nu prime. This is then j double prime square plus 2j double prime plus j double prime plus of 2 minus b nu double prime of j double prime square plus of j double prime. Now you rearrange these terms. This nu naught plus of 2 of b nu prime, 2 nu prime, plus 2j, then this is a 2 from 2 over here, and j double prime from here, then this is the 3 of b nu prime minus this j double prime over from there, then you have a b of nu double prime of j double prime, that is the first order term, plus of b of nu prime, this term, minus b of nu double prime of j double prime square, where the z double prime, the lower rotational quantum number, can taken the values of 0, 1, 2, 3. Now, as I said that this quantity, the z double prime can take a value 0, 1, 2, 3, so and so on. So, this z double prime is equal to 0, 1, 2, and 3, and so on. So, it means that this R branch, the series of lines named at R0, so corresponding to J double prime is equal to 0, I would have simply this R of 0, R of 1, and R of 2. These are the lines corresponding to the value of J double prime equal to 0, 1, 2, 3, and so on. And J double prime on the higher wave number side of the bend origin. So once you have a bend origin, that is the corresponding to this new one, then higher bend side. Now I know that since this b of nu prime is less than to this b of nu double prime, it means that this b of nu prime minus b nu double prime is always negative quantity. If you look at this quantity is a negative quantity. This is because this is 3 times of this one, you may have some positive quantity in this case. But it is a slightly, this v nu is a 3b prime minus b of nu double prime is as positive as b nu of prime is only slightly smaller than b nu double prime. Thus the linear and the quadratic term on equation 1 are opposite signs. Hence the line spacing decreases very slowly as j takes an increasing value. So what I am saying that at this point, this quantity is negative and this quantity is slightly positive. Now these are the reverse terms. Then once this j is increasing, then the spacing between the lines is slowly decreasing as the j double prime value is decreasing. So once I will be this energy diagram we are plotting now, we'll see that so I have this one level is over here and another level is here. This is a new double prime is equal to 0 and a new prime is equal to 1. Now you have this z, that is the z 0, 0, 1, 0, 1, 2, 3, 4, 5. These are the z double prime, that is 1, 2, 3, 4 and 5. And similarly you have these are the values of z prime, 0, 1, 2, 3, 4 and 5. So you have a pure vibrational state, that is the transition between this, that is the band origin. Now as I said that for the R branch who are slightly higher wave number side, this transition is taking place, means 0 to 1. This is 0 to 1, that is a plus z, this delta z, z prime is equal to z double prime plus of 1. Then another level is this one, another level is this one, another level is this one, another level is this one. So once we this one. Now once you are moving for the higher value of the z, the separation between these lines will be decreasing. Now let me discuss about first this P branch now. P branch. In this case delta z is equal to -1. It means that this z prime minus z double prime is equal to -1, so that this z double prime is equal to z double prime minus of 1. In this case, now this nu of P branch is equal to nu naught plus of B nu prime, this z double prime minus of 1, this z double prime, minus B nu double prime, the z double prime of z double prime plus of 1. So is equal to simply this nu naught plus of v nu prime of z double prime square minus of z double prime minus b nu double prime of z double prime plus of z double prime is equal to nu naught plus this is a minus term, right? This is a minus of b nu prime from here, this is z double prime, from here this is minus z prime again, this minus of b nu double prime of z double prime, then you have a square term, again you have a square term, then plus of b of nu prime minus b nu double prime of z double prime of square. Now in this relation, if you look at equation number 2, z double prime is the lower rotational quantum number and j double prime cannot be 0 because this level j prime is equal to -1. So it doesn't exist, because once I will be putting that z is equal to 0, then you have a -1. Then this j single prime -1 doesn't exist. That is the minimum value of this quantum number j prime is equal to 0. So the value of z double prime are allowed, this 1, 2 and 3 and so on, because the transition cannot take place at negative energy levels. It doesn't exist. So now if you look at, now in this relation again you need to check that this v of nu prime is less than to this b nu double prime. This quantity is less than to this quantity, right? So this I am getting this negative 1. This again I have a negative 1. So this quantity, already this is plus 1, these are the plus, then I have a negative sign, and this is a negative sign. So both the linear and the quadratic terms in equation second number 2 are now the same sign of that, the lines of the other branch. So it means that this, as the j value is increasing, the lines with these rotational lines, the p branch lines, are separating out. Means the distance, as in this case we have this separation between lines is decreasing as j is equal to increasing. In this case it is the separation is increasing. So now once I know that in the case of the p branch, for the p branch I have this p of 1, p of 2 and p of 3 and so on, because this z double prime is equal to 0 value doesn't allow in this case. Now once I will put plotting, so now in this case now what will happen, that minus 1 means that is 0 from 1 to, you have the transition is from 1 to 0. Transition is 1 to 0, 2 to 1, and 3 to 4, 3 to 2, and 3 to 2, and 4 to 3, 4 to 3, and 5 to 4. These are the allowed. These are my, this is my P5, P4, P3, P2 and P of 1. In this case, this R of 0, R of 1, R of 2, R of 3 and so on. The separation, these lines are the higher wave number side are decreasing, this side is increasing, because from both the relations you have this justification for them. So now these are called the P branch and the R branch. So if you neglect the vibration rotation interactions, so because we have considered that there is an interaction between, now it means that there is independent values. We haven't taken the value of B for the two different vibrational levels are the same, they are entirely different. It means that there is a rotation, this is an interaction between them. It means what we have defined, that this is V of nu prime is not equal to this V nu double prime. It means that some interaction is taking place. Now if we are ignoring this V nu prime is equal to V nu double prime, interaction is called independent to each other, then simply the R branch and the P branch you can represent with the help of this nu R is equal to this nu naught plus of 2 of B plus 2B of J double prime from equation number 1 and 2, and nu of P is equal to nu naught minus of 2B of J double prime. Both the branches would have a equilines, equidistance, now equal spacing in the both the lines now. Here you have a from this 0 plus 2b and this 2b. Now this is the 0 line, because once you are putting this 0, then it's just simply this 2b. Then you have over here. On the other hand, on this z double prime cannot be my 0. The z double prime cannot be 0 in the P branch, at least it is a 1. Then you have this is 2p. So now you have a equidistance separation between these two lines. Once you are not considering that the interaction between this vibrational and the rotational spectra. So from equation number 1 and 2 we have this one. Since the two branches have the common upper and the lower states, they must be interrelated. In fact, they can be fitted to the same parabolic equation. So what we have, now we are defining this with the help of equation number 1 and 2. So I could write this nu is equal to nu naught plus b of nu prime minus plus of b nu double prime of m plus b of nu prime minus of b nu double prime and m square, equation number 3. So now I'm writing that this same parabolic equation either for the P branch and the R branch. So if you look at both the cases, either you have a value of the m positive and the negative. These coefficients are v nu prime plus or v nu double prime and v nu prime minus v nu double prime. In both the cases you have this parabolic relation. Now where we can define that, where this m is equal to z double prime plus of 1 is equal to 1, 2, 3 and so on for lines R0, R1, R2 and so on. Now once you are modeling this equation, once you are putting the value of m, j prime double prime plus of 1 in this equation, then you will be getting that the first equation that corresponding to that you have this nu of r. On the other hand, once you are putting that the value of m is equal to minus z double prime, where this value of m is equal to minus 1, minus 2, minus 3 and so on. For the lines, this p of 1, this p of 2, p of 3 and so on. So with the same parabolic equations, we have defined as two lines for this R branch and the P branch. Now in this case for the P branch, you need to put this value of m is equal to z double prime plus of 1. And this is m is equal to minus z double prime for the P branch. From the same equation, once you are putting the value of these in this equation, then you will be getting that equation number 1 and 2 corresponding to your R branch and the P branch. If m is equal to 0 for the 0 gap. And once you are putting the m is equal to 0, then m is equal to 0, you have pure rotational spectra, this term becoming 0, then you have nu is equal to nu naught, that is the pure vibrational changes. So once I will be plotting this equation, once you will plot this equation, so I will be plotting that this value of m in a y-axis, this is the m plus 1, this is the plus 1, plus 2, plus 3, plus 4 and so on, minus 1, minus 2, minus 3, minus 4 and so on. Right? And this is my nu, frequency nu. So you have somewhere here, this is a nu naught, where the value of m is equal to 0, you have this nu naught. You have some finite value of nu naught. So once you are going for the positive value of this, say this m, I have this P branch. So you have some so once you are going for the negative values, then you have a P branch, and once you are going for the positive cases, then this is a R branch. So you have this parabolic equation. It is not a linear relation. If you would have this nu prime is equal to b nu prime is equal to b or nu double prime, then you would have a straight line. This is not a case slightly because these are the parabolic equations. Then you can write. Then you have this kind of plot for this relation. So once these are the spectra, these are the relations for the P branch and R branch, and this is the line. If I would have, there is no interaction between the linear relation, that is linear relation, if you would have the independency of this interaction between the interaction between the vibration level and the rotational spectra. So now it is clear now from this side you have a spacing is reducing as you are going this side, and you are going this side, you have a spacing is reducing. Since the constant alpha is very small, the difference this v of nu minus is also very small, means alpha e is very small. It means that this v nu prime minus v nu double prime is very small. Hence the curve is only very slightly deviated from the straight line. This is why the vibration rotational bands show a very poor tendency to the head formation. So this is very, these values are very small. So this shows a very weak tendency of the head formation. And what does it mean that the head formation? Exactly, vibration rotational band, both the involved vibration levels belongs to the same electronic state. Now, once I am dealing this nu double prime is equal to 0, nu prime is equal to 1, these both are belonging to the same electronic state, within the same electronic state. Therefore, the rotational constant for the upper vibrational state, V nu prime, is always smaller than that of the lower vibrational state. And since, why it is, since that R of E is always greater than this R of nu double prime. And we know that this V is 1 proportional to 1 upon R E of square. That is the, now we have defined this average value of this one. Hence, that parabolic equation shows that the spacing decreases at takes the increasing positive value. That is, the spacing decreases, and this means that the tendency to the head formation is always seen in the R branch. Conversely, the degradation of the bands of the observed in the P branch means that head formation if there is a dense transition, dense lines you have done, dense transition lines are taking place, because the spacing is reducing. It means that this side will be getting that the dense lines. So that is called the head formation. On the other hand, once you are looking for this side, this, because the density of these are separating out these lines, it means that you won't be getting the head formation for the P branch. So, and thus it may be expressed that by saying that these rotation vibration bands are always degraded towards the lower wave number, degraded lower wave numbers side, that is the towards the red end. And in contrast, electronic bands show that the strong tendency of head formation and may be degraded either way. So we'll see that in the case of electronic spectra, we'll see that it having a strong tendency to form a head. Now this is all about this my molecule as a vibrational rotator, and we have considered as for that there is a independent interactions. Then you have just putting these two linearly, you are adding these energies. However, once the observations are taken place, once the observation is measured, then these spectral lines within a band, these spectral lines are not equidistant, rather they are in a particular fashion. Now it means that there are two independent vibrational levels are within these vibrational levels. You have the rotational lines, and these are interacting with each other. Then this rotational constant is changing for the two different vibrational levels. Then finally we achieved that the P R branch and the P branch. I believe that it is, this is very important, and this is appeared in the 2018 and the 17 question papers. If you have a question papers, and just look at this P branch and the R branch, what exactly you have in a molecule as a vibrational rotator. And more importantly, we haven't discussed about this delta Z is equal to 0, where you have a pure lines corresponding to this one, that is the band origin. And we'll see that these are, if this delta Z is equal to 0, if the transition is taking place, then this is the Q branch of the vibrational rotator. So now, in the next class, I will be discussing about this Raman spectrum, and we will be going to the electronic state. And for the Raman spectra, we will be discussing that is the classical assumption, classical expansion, and the quantum mechanical. So for today's class, it's I'm stopping at this point, and we'll see that what we can do for that, and how we can explain. We need to go through these electronic states. Then before that, I'll be discussing about the Raman spectra. Why this Raman spectra is important. If you remember that In the case of the vibration and the rotational, there is a primary condition that this diatomic molecule must be having the permanent dipole moment. Okay. Thank you.